All right, so we're coming back to chapter 8 now. So let's get back into it. We're looking at chapter 8. And so I'm going to start with a kind of a motivation here. And so we are on page approximately 13 in the workbook. All right. And so what we're going to do now is create a new mathematical construct to reduce the amount of effort required to solve problems. At first, this is probably going to seem a little silly. It'll feel a little bit like a circular reference. It might even be confusing. But in the long run, after you do a bunch of problems from chapter 8, you're going to discover you love doing problems with this new style using potential energy instead of always doing work. Now, first, I want to mention a thing called conserve energy. So, when we talk about conserving energy when we're at home with our family or friends, usually that means turn off the lights so you're not wasting energy. In physics, conserving energy simply means the initial energy and the final energy is you're not losing any energy to the system. So that's what we mean in a physics system. So, strictly speaking, here's the physics definition. Gravity and springs do no net work for any closed path. Maybe you should underline this word any. All right. So a closed path, what does that mean? That is a path that starts and stops at the same point. For example, if you walk to the right 3 meters and then come right back, or if you go up and down or walk around in a circle. All right. So now, if you have a force that is conservative, work is defined as opposite the change in potential energy. Or strictly speaking, I should say the change in potential energy is negative U. Change in potential energy is negative work. So, for example, let's start with this line of the equation. The change in potential energy associated with gravity, whatever that is, by definition is given by minus the work done by gravity. Okay? So imagine we're starting right here. Okay? And we're going to go this direction from start to finish. Well, the work done by gravity would be mgh. Now let's think about this. The object is going downwards. Gravity should try and speed it up. It makes sense that that work done as I go downwards by gravity should be positive. That's why the term inside is positive. The minus sign comes from the definition. Notice the change in potential energy as you go downwards should be negative mgh. Now, when we are doing energy problems, we are free to choose our coordinate system. We could set the bottom equal to 0. We could also set the top equal to 0. But the idea here is the change in position is always negative h, regardless of how we get there. Let me just put that here because it's kind of hard to see. The change in vertical position is negative h. And that's true whether you call the top 6 or pi or 18n, where n could be your breakout room number. It could be any weird thing you want. But the idea is the change in height is always the same. This is a big deal. Now, that said, usually we will try to pick the lowest point in our problem to be y equals 0. Not always. There are certain times that's not a good choice. Springs, for example. All right. When you do that, notice if we do this, we could set the potential energy at the bottom to 0. And when you do that, we get this weird equation. We see that the potential energy, I need just a little bit more space here. Let me scroll down. Associated with a given height is mgh. So, all right, let me summarize here what this is trying to say. Okay. Effectively, we have just seen for gravitational problems, we see that gravitational energy can be given by as mgh, where h is height above reference level. That's your height above a reference level. So you get to choose the reference level. Delta U is given by mg delta h, the change in vertical. And I guess I could be careful here, say mgy delta y, where this is your vertical displacement. Notice it could be positive or negative. So you could have a positive or negative change in U. This is not the same as work. And in fact, we just saw the change in potential energy is opposite the work done by gravity. All right. Okay. So those are just some definitions. Any questions about those definitions right away? Let's see if there's anything else I want to say on there. Later on in chapter 13, we'll extend this definition, and actually this one will extend to astronomical bodies, and it's a little bit different there, but let's worry about that then. All right, so here's the cool thing about this. If we do this right now, we could now treat problems a different way. So it turns out, previously, we said that the work net is equal to the change in kinetic energy only. This is called the work energy theorem. Now, what we could do is we could say E initial plus work done by non-conservative and external forces is equal to E final. Whoa, this looks like a long, painful thing, but it's actually not that bad. So here, I don't know if you remember, I said gravity is a force which conserves energy. When I lift something up and bring it right back down, it does the same amount of work. And that's true whether I do it diagonally or around in a circle or any different path. So by definition, gravity is conservative. That means I don't need to calculate the work done by it anymore. That's the advantage. Okay. Springs act the same way. Friction, unfortunately, does not conserve energy, right? The work done by friction, if I raise a block up a ramp and then bring it back down, oftentimes friction is working against me on the way up and it's working against me on the way down. So the work done by friction there would be negative. So we see that the work done by some forces does not conserve energy, and friction is one of them. But if we could do this right, it usually turns out where we get U due to gravity plus U from a spring plus kinetic energy initial plus work done by, I'm going to say NC/EXT is equal to UG final plus U spring final plus K final. Now, again, I'm going to put some subscripts on here, and I'm going to use color for that. This is the initial amount of energy. Whoops. And this is the final amount of energy of each type. And it turns out we've got some shortcut formulas on the back of our workbook for figuring out these things really quickly. And what we do is, in many problems, the external forces are negligible, or the non-conservative forces are negligible. If this term is negligible, so that's a big if, then what we say is E initial equals E final. Or we say in physics, energy is conserved. Sorry about that. So this is what conservation of energy means to a physicist. If energy is conserved, the initial amount of energy is equal to the final amount. Now we got to be careful. It could change from, like, maybe you start out with some gravitational energy and it turns into kinetic energy. Or maybe we have some combination of gravitational, spring, and kinetic, and it turns into a different combination of gravitational, spring, and kinetic. But the fact remains is, if this term is zero, again, a huge if there's no zombies and no friction, usually this term drops out and we say, okay, the initial and finals should equal. And that's a huge relationship we can use to analyze things like how fast is it moving? Because again, speed is in here. Or we could say, how high will it go? Right? Height is in here. Or how much will it squish a spring? Or how strong a spring do I need to stop the motion so people don't die on the roller coaster if the brakes give out? All kinds of different things you could use this calculation for. I'm going to pause there. This is very theoretical right now. We got to do some examples.
If you make the system big enough, aren't all forces aren't all forces conservative? Or
yeah, you could argue that energy is conserved in the universe. And actually, let me allude to this on the next page in the workbook. Good question. So let me scroll to the next page of the workbook. So now page 14. Let me get into this by just making. I'm going to answer your question in just a sec, Esteban.
No problem.
First, let me think about it like this: energy and money. This might also give people an idea, and then we could talk about what you just said. Imagine you have a checking and a savings account, right? You could imagine your checking account is one type of money and your savings account is a different type of money. For example, you could think of your savings account as potential energy and checking is kinetic. You could transfer back and forth between them. External would be having to pay your bills and send money to somebody else. And you could actually get a paycheck, which would be sweet. And you could dump that into your account. So notice it is possible that energy can enter or leave your bank accounts, and it won't just stay in your particular bank accounts. But if you're not getting deposits or making purchases, the energy or money inside your bank account is conserved. Now, from a practical standpoint, this is alluding to what Esteban was just asking about. This is what we're doing in chapter 8, right? So let's take a second to look at this. You pick a system. If your system was the entire universe, Esteban, you're absolutely right. Energy would be conserved in the universe. However, it is impractical to track every single atom in the universe to keep track of its temperature, right? And so if we could do that, though, we could actually keep track of the molecular motion of every single molecule in the universe. Sure, energy would be conserved all the time. But anytime you have heat, which is almost all the time, right? You rub your hands together, there's a little bit of friction. You could feel them emitting heat. Heat is energy transfer between objects. And so that energy usually goes into raising the temperature raising the temperature of objects. Or essentially, if you raise the temperature of an object, you're changing the internal motion of the molecules. That's nearly impossible for us to track. So Esteban, does that address your question?
Yes.
Yes. All right. So so what we oftentimes have to do is create a practical system here. And so we're going to assume like maybe there's a table, a spring, there's some internal strings, but there could be a giant space zombie pulling something. There could be energy leaving the system. That would be stuff we try to account for here. Hopefully, most of the time this will be negligible, or there's a simple way to account for it. And if that's true, if we can account for this, we can relate the initial energy to the final energy by how much work comes into or out of our system. That is the chapter 8 style. So what do we typically do? The force of gravity and springs, we don't do work for those anymore. Instead of doing work, we're going to do spring potential energy and gravitational potential energy. That's U sub spring and U sub G. Now, if there are things like friction or space zombies, we could account for those doing the chapter 7 method. You draw an FBD, do this equation, and do what we just did in chapter 7. That's our new style. To compare that, how did we do this before? In chapter 7, what we'd have to do is first get the work done by gravity, then the work done by the spring, then the work done by friction, then the work done by the space zombie tension, and we'd set that equal to delta K. The math of it ends up exactly the same. The only difference here is in chapter 7, we do work done by gravity and work done by the spring. In chapter 8, we do not do that. We do the energy equations instead. And pretty soon, you are going to love chapter 8 and basically do it everything with the chapter 8 style instead. So questions about that? It's just the two styles. They're both, yeah. All right.
So that's just because the work by the spring and gravity just end up being zero, right?
Well, remember, the gravitational potential energy, by definition, was already accounting for the work, right? Delta U of gravitation, by definition, is minus the work done by gravity. So if you do the work done by gravity and the potential energy from gravity, you're double counting its work. Did that address your question, or did I not understand the question?
No, so in the second style where we
Yep.
did it using chapter 7,
Yep.
because what I'm trying to understand is, so the work done by gravity and the work done by spring, don't those end up being zero because, like you said, they're conservative?
They're only zero if you start and end at the same spot.
Oh, okay.
Right? So a conservative force is one when the work is zero if you return to your starting point.
Oh, okay. Got it. Okay.
So yeah, now it's quite possible that that is applicable in some random problem, but it's also possible that it's not.
Right, and so that's where chapter 8 comes in more handy.
Yep. Okay, so let's see if we could summarize the takeaways from all this crap. In the entire universe, E initial equals E final. Unfortunately, it's impossible for us to do that in the real world because it's improper. We can't get all the molecules. Great. So in many systems, we're going to use this situation. There's energy either entering or leaving the system. And again, summarizing, we're either going to do work done by gravity and work done by spring, or GP and SP, but not both, because they're essentially the same thing. And here we go. For conservative forces, we could use this delta U equals negative work. These are our typical energies. Okay, there's translational kinetic energy. We've been calling that K. But now I want to clue you in. Chapter 10, we will also discuss there's a rotational kinetic energy. You don't need to worry about this rotational until chapter 10. So forget about it for now. There's spring potential energy, and there's gravitational potential energy. Okay, these are the formulas. They're on the back of your book as well. For a lot of problems, we're going to have sliding friction, gravity, and springs. If you're doing chapter 7, you do what we just said. Get the work from every force acting on the object and do this. If we're doing chapter 8, we're going to use potential energy instead of work. And so our equations often end up looking like this big blob right here. And then I say in special cases, friction does no work, or sometimes it could do positive work. Who knows? But and if you have external tension from a zombie or something, you'd add in a work done by tension term. So this is the equation we're going to use over and over and over again for the most part. And so once you get used to it, it's super fast. All right. Oh, here's a weird technical note. The gravitational energy is actually shared between the Earth and whatever object it is. However, usually what moves more? Like if you have a ball and the Earth and you drop a ball, technically the Earth does come up to meet it, but the emotion associated with the Earth is so negligible, it's ridiculous. So, and I don't know if you remember, because there's a V squared, if the speed of the Earth is so tiny, then you square it, it's really tiny. So ignoring the kinetic energy associated with the Earth is typical in these problems. All right. Whoops. Let me see here. I'm going to try and give you an example here, a visual example. Give me just a second. Whoops, wrong button. Okay, let's hit this and do this. Whoops, where did it go? There we go. All right. And so let's go to this one. All right. And so what I'm going to do is I'm going to set the friction to 0 initially. Now, in this problem, this is going to seem a little bit crazy, but right now, this person, I hit the pause button. This is supposed to represent the center of this person's mass. Now, obviously, it's not really at the bottom, but this just simplifies the simulation and the code and everything. So just pretend we're looking at an object with negligible size, or if you like it, imagine the wheels of the skateboard are 10 miles long and made of depleted uranium. So the center of mass is basically right between the wheels, okay? So we've got a very strange skateboard. And now what I'm going to do is I'm going to put this person over here. And now again, it's paused, and I'm going to hit slow motion for a second. And what I want to do is show, well, let's look at the bar graph. Right now, the person is not moving. Okay. So right now, notice there's no kinetic energy. If it helps, remember the kinetic energy formula is 1/2 mv squared. And the potential energy due to gravity, we don't have any springs. The formula that we're going to use for that is mgh. And now, just so I could see a little bit better, let me put the grid on here. So again, we're focused on this red dot. This is the starting level. Okay, the person's at that red dot. If I hit play, in theory, if there's no friction, again, we're looking here at the friction. There's no friction right now. When I run this one, how far should the person get to the other side? How high up should the person go on the other side? Same height. So this seems reasonable. Watch this. If I go right here, look at the energy bar graphs right now. I hit pause. So again, look at the energy bar graphs on this side of the screen. And notice right now, what we've done is we've converted most of the potential into kinetic. But look at this. The total energy is unchanged. So again, if the bearings on the skateboard are very good, if air resistance is negligible, if we're not worried about the track itself getting warmed up from the frictional forces, this is all working out great. So let's keep going. Let me hit play. Notice right at the bottom, there's no potential energy. It's all kinetic. And as it rises to the top, that converts back. Look at this cool step right here, right about there. There's equal amounts of potential and kinetic. So it should be, I think, exactly at about 2.5, but whatever. Oops, let's just keep playing here. All right, and so there we go. Now, what's going to happen if I add in friction? I'm going to add in a little bit of friction, and this is reality now. So I'll wait till she gets to the top. Now I'm going to add in some friction. In the real world, when there's friction, notice a tiny bit of energy gets used up. And so if I just speed this up to normal speed, over time, energy leaves a system in the real world because of friction here. And we see that the largest part of the friction is happening right at the bottom. And so over time, you bet this person is not going to skate perfectly as high anymore. All right. Now, I don't know. Any questions about this while this is running? There's still the same amount of total energy as the beginning. However, this thermal energy, we can't use it, right? That's lost to the internal energy of molecules in the skateboard wheels and the track. All right. So, all right, that's a classic. Let me try one here. I've got a video here. Got on the wrong account. Let's do this one. sorry. I've got a little puzzle for you. Shoot, where is that one? Oh, I got to go to my channel too. Sorry. Sorry, this is taking so long. Let's see, where is that one? I think I've got it right here. Ah, no. There we go. All right. So in this case, let's consider this video here. So what I'm going to do is I'm going to swing this pendulum, and let me make it full screen for a second and mute it. Okay. So now what I'm going to do is I'm going to mix this up. Instead of the skateboarder swinging back and forth, I don't know if you can see this, but there's a rod right here. So this swing, this pendulum is going to swing, and right here, it's going to hit this rod and it's going to swing up. So my question is, do you think the angle that it swings up to will be greater than, less than, or equal to the initial angle? So let's say we call this theta, and let's just eyeball it. It looks to me like it's almost exactly 45 degrees or something. So let's say theta initial equals 45 degrees. What do you think will be true about theta final? Will it be greater than, less than, or equal to theta initial? What's your gut tell you?
Will it be greater than?
Okay, and then, all right, so let's take a look and see. And let me actually erase some of this stuff. Sorry. Let me get rid of this. So let's watch this thing and see what happens. And it's going to happen quickly, so I might actually slow it down just a little bit. And so I don't know if you could see this. It's coming almost exactly to the same spot on each end. And so the angle changes. This is an example of showing you there's very little friction in this system. There's a little bit. It's slowly starting to decay there. But that was one example of this one. Whoa, we don't want to go to this one yet. Let me escape out of here. Let's try another one. Let's try this one. High load, low load. High road, low road. So in this particular example, let me clear this out. Whoops, annotate, clear. In this particular example, it's very difficult to see, but there's a green track and a blue track and an orange track. So just to note those out, this orange one is the high road. And then this cyan one down here is the low road. And I've got two spheres over here, and I'm going to release them from rest at the same time. Which sphere should win the race? Should it be the high road or the low road? Or you could say the orange one or the blue one. What do you think? Take a second to kind of think it through.
I think they'll be the same.
Okay, and what's your logic on that?
I'm seeing the low road is going to gain speed, but then it's going to lose the speed as it goes up the thing, so it's going to be the same.
Okay, so you just said, I think you said V final, we'll say low, should equal V final high, right?
Yeah.
All right. That seems reasonable. However, what you said is just true, but that doesn't necessarily, just because they're moving the same speed at the end, doesn't mean they tie. Agreed? Let's see what happens. Notice the low road, and now it's not perfect here, but within error tolerance, these two balls are actually going about the same speed. There's a little bit of error associated with aligning these photo gates here. So I did this experiment many, many times, and essentially the final speeds are approximately tied within the quality of within the precision of my measurements. And it seems pretty reasonable. So this is a check on your answer. They do finish at the same speed is what I'm telling you there. However, look at this section of the track, right? If we watch this again in slow motion, you will see the ball actually covers this section of the track faster than that one. And so it gets ahead during that time. And you could even talk about the independence of XY motion, right? You could, on this section of the track, on these angled sections of the track, we could actually talk about the independence of the X and Y motion and blah, blah, blah. But yeah, anyways, we see that at least in this case, the low road actually wins by a decent margin. So let's clear that out and watch it one more time in slow-mo. Here we go. Pretty much released at the rest at the same time. There we see the bottom one gets ahead. And so that's kind of cool. All right. So now, oh, there, the ball went flying there. So in this case, whoops, I should stop that video so it stops. Okay, let me pause that and let me get out of here. Sorry. All right. And get back to Zoom. Oh my gosh, so many windows. Make sure that's paused. Yeah, it is. Okay. All right. Esteban, is that good for you on that one?
Yeah, it kind of reminds me of when I used to ride my bike on the levee. I used to go down the ramp to try to pick up speed to think that I could get ahead, and I would go down the ramp and pick up speed and then go back up the ramp to get back on the levee, and I'll end up in the same spot as the person I was riding with.
Yeah, and so there are limits to this. And now I know this is, I don't know, this to me is kind of fun. I don't know if you've ever heard of this word, but well, hold on. Let me get the board erased so we could talk. I hope you agree that this won't always work. Like, let me give you an example. Let's say we go like this, and this is track 1. Okay, so we'll say this is the high road. And let's say the low road looks like this. And just so you could see it, what if we did this? I hope you agree. Even if it was in free fall here, at some point you could make this track long enough that the time to fall down would be longer than the time for this one to complete the race. So clearly this is not always true that the low road should win. And that might be what Esteban was experiencing. Sometimes the low road is slower because it takes you so long to get to the lower track that even if you're going faster here, and even if you're going a lot faster, it still does you no good because it takes so much time to go up and down. So we see already that this is not the fastest path. This is not the fastest path. There is some path that is the fastest. Does anybody know the name for that path? The path which requires the least time to travel between 2 points.
A straight line?
No.
Huh.
At least not on Earth or anywhere there's a gravitational field, right? This is closer to a straight line than this. We know that some dip is worth it, right? Now I'm going to kind of exaggerate this, right? So there's some shape in here where it takes a dip that's not a straight line, that's faster. So it's not straight line path. That's a good path. And this is even true if you were on an angle. Like you could go this way. It turns out this path would probably do better. If you don't believe me, think about it. If you start here on these high tracks and this lower track, which one is going to accelerate faster initially? The high road or the low road in this case? Which one will accelerate more rapidly?
Low road.
Low road. So this lower road is going to pick up speed rapidly. And then, true, it has more distance to cover, but it's covering most of that distance at a dramatically faster speed. Look, by the time this one gets down here, it might be going twice as fast. So it could easily cover this extra distance. Okay, the path of least time is called a bra brachistochrone. Let me see if I brachistochrone. Chronos, time. You know, I have so much trouble saying this word, brachistochrone. So in this case, this means path of least time. It turns out the math behind this relates to what's called the calculus of variations. You're lucky it's not on your test. There were two Bernoulli brothers. You can read about it. Supposedly there was a family feud, and maybe we could simulate this with Gage and Luke Franks, like saying, "Ha ha, calculate the path of least time." And then they could find out that it takes a new branch of mathematics to solve this problem. So let's, or we could just move on and focus on stuff that might be on the test. But so if you're interested in that, you could talk to me in office hours or whatever. I just find that interesting. The path of least time is the brachistochrone. All right. And let me see where I want to go next here. All right. So let me go back to the workbook here. So fortunately, we've got Wednesday and I think some of next week to cover this stuff. So it's okay if I slow play it a little bit and focus on the concepts right now, and at least in my opinion. So we kind of looked at a simulation just a minute ago and talked about this one. So if you're curious, this does the algebra of all of that problem here. So let's maybe take a look at this solution. So let's take a second to look at 8.3. This is the math behind the simulation that we just did before that gets away from us. Okay, we've got a block of, oh, whoops, there's an S missing there. Make a note of that. That's weird that that didn't show up. Whatever. Okay. The block has negligible size. Okay, so it's released from initial height h. So, okay. This, we're saying, is at some initial height. So we could say this is at y initial. Now, I want to be clear. If I'm doing a chapter 8 problem, the first thing I need to do is tell you where y equals 0 is. So we're saying y is equal to 0 at the bottom of the ramp. You don't have to choose it the same as me. You could say y equals 0 at the top, but then the bottom would be a negative height. Okay, right? It would be a negative vertical position, I should say carefully. So usually you pick the lowest point in a problem and set that to y equals 0. That is what allows me to say, well, fine, this is at some height y initial equals h. Okay, again, this is called setting your reference level. Always do it in an energy problem from chapter 8. Next, we could write down our equation. We've got k initial plus u due to gravity initial. Do you see any springs in this problem? No. I'm not even going to write the spring energy because we don't have any springs. Okay, there could be work done. So I'm going to include that, and I'm going to say work done by non-conservative forces or external forces like zombies, something like that. And then at the end, we're going to have K final plus U final. In this case, U due to gravity final. This is the math that we would write down for this problem. Again, it's okay to go slow, right? This is our first energy problem. I'm going to pause right here. Is everybody cool with this? This is our new style of doing problems. This is chapter 8 style. Okay. What is the initial kinetic energy? Maybe I'll write these formula over here so you have it. The formula for kinetic energy was 1/2 mv squared. And the potential energy due to gravity equation was mg h. Let's say mgy in this case, just because, yeah, that's what I chose to say. All right. What is the initial kinetic energy?
V0?
0. What's the key words?
Initial?
True. Or, yeah, how about that? Are you cool with that? It was released from rest initially, so it's 0 initially. And I think that's where you were going with it, right? All right, I'm going to assume so. All right. What's the initial gravitational potential energy?
MGH or
Absolutely.
MGY.
Yep. However you want to call it. In this case, we'll just say, yeah, cool. So notice I'm kind of being a little bit loosey-goosey with MGY and MGH. The idea that I used MGY over here on the left side is I want this to be true in general for any value of Y. And then in this particular problem, the value of Y is H. That's why it was okay to change MGY to MGH. I know that seems silly, whatever. All right. What's the final gravitational energy? What's your final height when the block slides to the bottom?
0.
0. So that one's 0. And then what's the equation for the final energy of kinetic? 1/2 mv final. Yep, V final. Now, this is always the thing that you run into trouble with. So let's check. Do we have any friction? No. No friction. Sweet. So there's no work done by friction. What about a zombie pulling on it with a rope? We don't have that. What about the ramp itself? Doesn't the ramp exert a force on the block? What are the forces on the block right here at this top position? Give me one force.
Normal force.
Normal force. You agree it's kind of like that direction-ish?
Yes.
And then what other force? We got gravity, right? Sorry, that's not perfect. There we go. Now, wait a minute. Don't we need to calculate the work done by gravity? Isn't that right? Is gravity doing work?
No.
Gravity is doing work, but we've already accounted for it. Do you see that? Does that make sense, that subtle distinction there?
Yeah.
Gravity does work. However, if we include it in the potential energy, we've already accounted for the work done by gravity. So I don't need to do the work done by gravity. What about the work done by the normal force?
Isn't it perpendicular? So that means it's 0?
Absolutely. So the work done by the normal force is 0 because perpendicular to displacement. And maybe I should say the normal force vector is perpendicular to displacement vector. Does that make sense? So after all of that, we get an equation that's very simple. After all of that, let's go to the solutions now. Whoop, geez, sorry. So this was what we start with. We have no non-conservative or external, right? The normal force is perpendicular. Gravity we've already accounted for. We get this result. And then very quickly, you could find the max speed is the square root of 2gh. That's amazing. And here's something else to notice. I know I'm going really slow here. I apologize. We will get faster later. But check this out. How many vectors did we have to split into components to get that answer? None. Isn't that cool? This is a different way of doing calculations that requires almost no vector math. The only time you have to do vector math is when you have this work non-conservative equals something other than 0. So for a large number of problems, we don't have to do any vectors and we can get speeds super fast. It's amazing. And once you get good at this, you probably wouldn't even write this first line. you would start going through it in your mind and say, look, there's no kinetic initial, there's mgh initial, there's kinetic final, but there's no gravity final. And you might get it to the point where you can literally write that equation with almost no effort, and you'll be so fast at getting these speeds, you'll love it. But it doesn't come for free. You have to practice. Questions about that? We see the speed at the bottom should depend on what planet you're on. That's G, which planet you're on, and H. All right. So let's go back to here. At what height above the ground does the block have half speed? So this is, okay, so what's your gut tell you? If you want half the speed, how far down do you need to go?
My gut tells me half the height, but it's probably wrong.
Exactly. You've learned that almost always your gut is wrong in physics at first. So let's do the math. Let's look at the solution to save ourselves some time. I say, okay, what I'm going to do is say the initial speed goes to 0. So let's just follow this line right here. Okay. Initial kinetic energy, initial gravitational. We already talked about the work non-conservative is 0. That goes right in there. There's none. And then the final speed and the final height. What are we trying to say here? We're saying let the final speed be half of the maximum value. And I have the same initial height and then solve for height final. And when you do this, notice it's 3/4. Right down there. Let me get that on screen. Okay, so you get the first half of the speed in the first quarter of the fall. That's crazy, right? Isn't that weird? Let's go take a look. Whoops, where is that one? No, this one. All right, so let's do a speed chart and let's get rid of friction. And let's start with this one. And so it looks like we're supposed to get fourths, right? So I'm going to run this one at in slow motion here. And so obviously right now the speed is 0. Whoops. Oh, let me hit play. That's about max speed. So I'm just going to mark this one. Oops, let me move something here. So this is 1, 2, 3, 4.5. So let's see, half speed should be about 2 1/4. So that's where we expect half speed to happen, right? So let's go see if I lied to you. Obviously, this is a simulation, so, but they're trying to code it the same way that I would as well. And notice we see that you get half the speed at 3/4 of the height. This is counterintuitive. Don't forget, it comes from the fact that you have a 1/2 mv squared. That squared is what's messing things up. So you could think about this as 1/2 squared, right? If we have half the speed, that gives you a fourth. And so it does actually seem logical that fourths come up in the answer. But it's very kind of uncomfortable feeling. Now, another way to think about this is, look, it's going so slow at the beginning. And then this last part, it's already going quite fast. So it's going to cover this distance more rapidly. It covers the last 3/4 of the distance more rapidly because it's already at speed. That means gravity is acting on it for less time. So even though the acceleration is essentially unchanged, it's going down almost at the same angle the whole way. Even though the gravitational acceleration doesn't change, because time is shorter for the last stage, the change in speed is less for the last 3/4, or well, I guess it's the same for the 3/4 versus 1/4. Whew. Questions on that? That's crazy, right? All right. Let me go to here. I'm going to show you a new idea. And so if you want, start taking a look in your book at problem 8.4. 8.4, everybody. I don't know if you could hear my stomach grumbling, but man, it's going nuts. Sorry about that. If you have to hear that, just hungry. I wonder if I could do, yeah, whatever. Maybe I could do this. Oops. There we go. Trying to make a circular track. Sorry it's taking me so long. This is not easy. All right, so we've got this situation here. Whoops. All right. So now my question is, we've got this skateboarder here, and it looks like, again, it's not perfect, but if we look at the center of mass of the skateboard as being at the wheels position, right? Down here at the bottom, this is effectively y equals 0. And up here, I hope you agree, it's not perfect, but the skateboard's approximately going to be at y equals 4 meters. All right. Which, interestingly enough, it looks like this girl skateboarder is about 2.1 meters. So she's probably in the women's NBA. That's an elite height level. All right. That's like 6'6" or something. All right. So in this case, here's the question I want to ask. Where do I need to put the skateboarder girl so that she makes it through the loop? What's your gut tell you?
At the very top.
Okay, so let me get my annotations out here. So if I put her up here at the very top at 8 and run this thing, looks like she makes it through no problem. Is there a lower height I could use? What is the lowest possible height? Oh, there's friction here. Crap. Let's take off the friction for right now and run this again. So she hopefully gets going a little bit faster now. But yeah, what's the lowest possible height you think we could use?
Is
And
it
again,
4?
Like 5.
So why do you say 4? What's your thought process?
Potential energy should be like the same.
Okay, you're absolutely right. Let's see what happens. You're absolutely right about the potential energy being the same. However, that's not going to work. Watch what happens. She's going, everything's fine. Oh, now I think right now, I don't know if you can see this on the right side of the screen. We have locked her feet to the track. Right now, I'm going to do it again, but I'm going to let her skateboard fall off the track. And as she gets close to the top, she's gone projectile. Oh, now, fortunately, she can miraculously invert herself. So that doesn't work. The issue is when you get to the top of the circle, if you're at the top of the circle, and if you're on the inside, let me do it like this. Whoops. Let's start up here. Sorry. She's at the top of the circle, and I'm going to pause it right now. Right now, this girl is actually moving this way, right? She's moving with some speed v. If her speed was 0, what would happen to her?
fall off.
And that's what we just saw. If your speed is too low, you fly off the track and become a projectile instead of actually making it up there. So we have to, does anybody remember the minimum speed for making it through a loop? Do you remember? Well, I'll tell you. We did this in chapter 6. Do you remember there was a square root of RG to get through? Like if you're swinging the bucket of water, right? I don't know if you remember this one. When you swing the bucket of water, the minimum speed to get through the loop at the top was square root of RG. Okay. And so it's not enough to start right here. Somebody else said 5. So in this case, let's see if that's going to do it. And so if you said that earlier, apologies, it took me so long to get there. So let's start it just above there. Okay. So in this case, if we run this, hopefully this should be about the lowest you can go to make this work. Just barely able. So now if we start here at just under that, you might see the girl start to projectile off the track here in just a second. See her go airborne? All right. And so that looks like it's about right. Now, personally, I don't believe a bunch of simulations all the time. So what I did is I made this video for you. And so in this case, hopefully you can watch this. I'm just going to play it and shut up here. So notice in this video right now, I think it's playing at low speed. But in this case, the ball is moving. It's I don't know if you could tell here. This is we'll call this 2 times the radius, that height, right? And so right here is about 2.5 times the radius, okay? So I'm going just below 2.5 times the radius. And when I run this thing, let's see. And this would match up to the last problem. Remember the radius in the last problem was 2. 2.5 times the radius was 5. So let's run this. You could see it has to go projectile. All right, so let's keep going here. So above that height, and again, sorry for the slow-mo. We see it doesn't come off the track. So we see that now notice, look at this huge amount of frictional loss in this problem. I hope you could agree there's actually the frictional losses here are non-zero because I started right about up here and I ended right here. So clearly this amount of energy was lost. I could calculate U initial using MGH initial. I could calculate U final using MGH final. And the difference between those two is how much energy was lost in one transit. So that's the change in energy. That would actually equal, in this case, the work done by those non-conservative and external. These things are not zero. In the real world, these things are present, but we often set them to zero to get a rough approximation. Okay, question about that. All right, cool. And I have no idea if this is painful or not. It probably is because I have no clue, but I just want to point out, if you're curious about this, here's the math. Yeah, so I did the math on it. And now, right now, we're talking about a problem where this slides. It turns out if you have to add the rolling energy, there's some energy with the ball spinning as well. And we will learn more about that later. So the trick here is if you don't remember that V equals the square root of RG, you do an FBD at point C. Let's look at it. Oh, there's another style. That's cool. All right, whatever. You could finish up that part. So what I did was, in this case, I said the height initial sorry. Let me get this picture up on the board here. All right. So we're not always going to do so much videos and simulation. So that was almost all the videos for this whole chapter. So the next time we're going to do grinding out problems. All right. So if you're worried that I'm not helping you enough, don't worry. I know we've got 2 more days at least of just grinding out example problems. So in this case, what I like to do, and you don't have to do it my way, you could do it whatever you want. But again, usually what I like to do is, unless there's a good reason otherwise, I call this y equals 0. The lowest point in the problem becomes my reference level. Why? I don't like dealing with negative positions if I can avoid it. Now, all my heights are going to be positive numbers. In this case, notice that this y is equal to 2 times the radius. It's not the radius, it's 2 times the radius. And so here, this y would equal height initial, or whatever you want to call it. And so we could have different height levels, and we could reference them to this being 0. So that's what I was trying to get at there. And so if you look on problem 8.4, sorry, getting to it in my workbook here. You could see that this is 0, this height is r, this height is 2r. That's the thing you've got to worry about. So going back to the solution. Okay, so point C was at height 2r. Notice we could get these speeds from an energy equation. And there's the swing the bucket of water problem. If it's about to lose contact at the top, we set the normal force equal to 0. So mg equals AC. From that, we get this minimum speed equals that. And notice if you stick all this junk into there, into here, we could discover that h min is 2.5 r. So that's where that value comes from. I'll let you guys kind of do the work on that later. Now, in this case, imagine you're a roller coaster engineer, all right? And so in this case, which loop has the greatest speed at the top? So we've got design A, B, and C. Which of those loops has the greatest speed at the top? Again, ignore friction and all that.
Are they all the same?
All the same. So we know that each one of these has the same height. That determines the speed. So it's a lot like that high road, low road we just did. So all same. Nice. So what about the accelerations? Will they all have the same acceleration? Are they accelerating at the top?
Do they all have 0 acceleration at the top?
One component of acceleration is 0 at the top. Which one?
The AY?
A tan. They're going in circles, right? Aha. We're assuming A tan is essentially equal to 0 at the top. However, are they all moving in circular motion?
No.
Yes. At any instant, any motion could be viewed as circular. They are doing this, and it's v squared over r. Now, why did you say no? Go ahead and say it.
They're not all in shapes of circles.
Exactly, but this one could be modeled as a big circle for that instant. Do you agree?
Yeah.
And this one could be modeled as a small circle at that instant. Aha! So use that information to rank the accelerations. Which one has the largest acceleration?
C.
Yeah, so it should be A for case C. That was a terrible. I should have called it design 1, 2, and 3 is greater than, what's the next one?
A,
A, and then followed by
B.
A, B. All right. Now, wait a minute. Let's do a normal force plus mg. And then that's going downwards. I'll call that A for right now. A centripetal. That's a lowercase c. Sorry, that lowercase and uppercase look similar. All right. But in this case, I hope you agree that N is equal to MAC minus mg. Do a little math. Notice the normal force is likely to be non-zero for design C, which means you're less likely to kill people. That's a good design, right? What do you think? It'll also make people more likely to puke. Also a design feature for a roller coaster. You're turning rapidly. So we see now that you can actually use this most basic knowledge you have of FBDs to actually start designing things with purpose. And that is what engineering's all about. And you're not going to be good at it now. You're going to be good at it in 5, 10, maybe 15 years, but you got to keep working at it. All right. I don't know. Any questions about that? I think that's cool. I don't know why, but yeah. There's probably more words in the solution. Let's see if there's something in there. Whoops. Let's go look at the solution, see if there's anything else in there that we'll probably pick up here next time, but whoops, this one. All right. So kind of, yeah, there we go. So that's great. Big deal. All right. Cool. All right. Projectiles. Turns out we've already talked about how to solve projectiles using another method, but you could actually do the same problems using energy, and you could get the same results. And in fact, you could go through them and show that the speed here is V initial squared plus 2gh and then square root of the whole thing. So if you want to do that, that's cool. What about springs? Okay, I'm going to derive this next time, but if you wanted to handle a spring, you just do the same type of problem here. Now, with springs, it gets tricky, especially vertical springs. And so we probably, well, I'm just going to foreshadow this a little bit. Let me just talk on the whiteboard for a minute, and then we'll call class after this. So how do we handle springs? Springs are the one case where I sometimes don't put the vertical position. Let me start over here. So this is effectively problem 8.10. So I'm going to say 8.10-ish, or just 8.10. Okay. Let's say we have a block here, and it's at rest. And then I'm going to drop it. I'm actually going to add another stage here. Here is right before impact. I hope you agree that this spring, or sorry, that this block is going to be moving downwards. I let go of it here. V initial was equal to 0. I dropped this block. Then eventually, hopefully you agree, if I was perfect at lining this thing up, the block is going to compress this spring some amount. And when the spring is compressed, the maximum amount, how fast is it moving?
0.
0. Think about it. It's going downwards, and then it slows down to a stop, and then the spring's going to push it back up. So right at the maximum compression, we know that the speed here, I guess we're just going to do this problem because it's so quick. Now check this out. For these types of problems, I often set this as y equals 0. This, In the problem 8.10 is height h. This right here, I'm having trouble fitting this all in. Let me squeeze it in here. So at maximum compression, this is 0. And notice this is some distance. You could call this y final equals negative d, or you could call it whatever you want. Yeah, it didn't specify. So you could call this negative d. Sometimes people call it negative x. Now, again, watch carefully. Why is it negative? It's because it's below y equals 0. So that's the part that matters. Okay. And so in this case, I know it's time to go, but I'm just going to screen share the solution and show you. So if you need to get out of here, that's fine. But if we could look at it really quick, what problem is this? 10? All right. And so if you look at this, oh, it looks like I used negative x in here. But so I've kind of got this drawn out for you. You could see that, okay, the initial goes to 0. It was released from rest. The initial height we called h. And then the initial spring energy was 0 because it's not touching the spring yet. At the end, velocity is again equal to 0. The height final is negative x. And then the distance it gets squished, 1/2 kx squared. This is the spring energy. Now we see there's an x squared in here. And so if we wanted to find the spring constant, this would be one way to do it. All right. And then here's a weird little note. You might be worried about the normal force, right? The normal force between the block and the platform is internal. So we don't have to worry about an internal work done by that normal force. Whew. So I'm going to go ahead and stop there. We could pick up here next time, but this just gives you an idea of where we're going with this. All right. So